Yes, in the last video we qualitatively looked at what it means to be negatively or positively correlated. And we looked at examples for one or the other, such as height and weight. When one is large, the other is typically large as well. This would be an example of positive correlation. The negative example was outdoor temperature and heating costs. When one is large, the other is small, and vice versa. What we want to do now is to define the whole thing mathematically, and in the end, have the ability to calculate it in a concrete example. And for that, we will now take a look at this definition here. Don't be alarmed. It's relatively large, but we will go through it step by step. So we start by stating that we have value pairs xi to x and y. So imagine that we have data here, x, x, and so on. For example, height and weight, I, and so on, would then be the other points. Yes, there are just as many. For each person there are, for example, 2 of these points. And now we want to ensure that the x's and the y's are not all the same. This is essentially for technical reasons, because we want the variance to not be 0 or the standard deviation to not be 0, as we still want to divide by them. And as mentioned, 1 obviously does not want to divide by 0. Well, now we define the so-called empirical correlation coefficient, or also the Pearson correlation coefficient. Pearson is the name of a mathematician named Pearson from whom the coefficient actually derives. And we usually denote it with the symbol R, Rx, Y. So the xy in the time index stands for the data x and the data y. And essentially, it is a quotient of 2 expressions. This one here and this one here. The denominator, we already know that. It is simply the standard deviations. And the numerator, we don't know that yet, that's the covariance. I'll write it down. And we want to take a look at that in the next step. We can see it here. This is the covariance, or also empirical covariance, because it concerns samples. And to understand that, I would briefly describe how variance was defined once again. That was s squared, and we could write it as 1 over n1, and then we formed the sum of xi, x. Then we have written a square here. However, I could also write the square by simply writing this factor twice again. And now we see that covariance is almost like variance, except that here we write y instead of x, and then we have covariance. Covariance is the number that describes exactly this. When it is negative, it indicates that when one is large, the other is small, and when it is positive, it means that when one is large, the other is also large. This means that the sign of this covariance ultimately determines the qualitative nature of the relationship. And I want to briefly discuss the relationship between the sign of the covariance, that is this term here, and that of the empirical correlation coefficient, which is this term here. That is actually the same sign, simply because they only differ in that I divide by the standard deviations in one case. However, the standard deviations are positive, meaning they do not change the sign, and thus both have the same sign. You might then wonder, why do we divide by the standard deviation again? It is a kind of normalization, because when we divide by this standard deviation, we can ensure that Rxe only has values between -1 and 1. And this has a certain advantage, as we can better compare correlation coefficients when they all lie within the same range of values. Yes, and we want to dedicate ourselves to a sentence that essentially describes what I have already said, namely, that this correlation coefficient lies exactly between -1 and 1, so the absolute value is less than or equal to 1. And the sentence also describes what happens when the value is actually -1 or 1, which represents the extreme case, so to speak. And the extreme case is that there is an exact, precisely linear relationship between x and y. And that means that the value pairs actually lie exactly on a straight line. And more specifically, when the value is +1, there is indeed this clear linear relationship between y and x. And if it is positive, then this relationship is such that the slope k is positive, and thus the values lie on a line that has a positive slope, meaning it goes upwards. And if the value is -1, then there is again a linear relationship, but this time with a slope of -2001, and perhaps it doesn't have, so to speak, significance, how large this slope is, meaning how steep the line is on which these points lie. It is simply about how close one is to an exact line, essentially exactly. And in the next example, we will look at how to actually calculate examples, how to approach it, and exactly what it means to represent a linear relationship. Until then, take care, use and